Finally now, it's fun time. We're going to discuss some applications of degree of maps of sphere. In this video, we're going to use degree to study fixed points of maps of sphere. In particular, we'll show that if a map F between sphere has no fixed point, then its degree must be equal to -1 to the n plus 1. This will then in turn allow us to classify all fixed point free action on the even sphere. In particular, we'll see that the only group that acts freely on the even sphere is the group Z mod 2Z, acting by reflection. So that's the overview of the story. Now, let's prove this first claim. Here we want to recall our previous result. Remember, degree of the antipodal map is equal to -1 to the n plus 1. Thus, it suffices to show that if F has no fixed point, then F must be homotopic to the antipodal map. And this is what we will prove. Alright, so let us suppose that F has no fixed point. We want to construct a homotopy between F and the antipodal map. The idea is to use a line homotopy. For every point P, we want FTP to be a point on this line segment, going from FP to the antipodal point of P, which we call -P. Well, I guess we do know how to do a straight line homotopy. This is just a beginner stuff. So is this the answer then? Is this the construction of the homotopy? Well, what is wrong with this answer? Observe that for these map Ft in this family, their images do not lie in Sn, because the norm of this is not necessarily 1. So to ensure that this image lies inside Sn, we'll need to divide this by its norm. Is this now a good answer? Well, there is one issue. How do we know that this norm will never be 0? We can't divide by 0, right? So what if this line segment actually crossed through the origin for some time t? Well, here is where we use the fact that Fp is not equal to P. Recall that all of these points must lie on the sphere, and the line through the origin and this antipodal point -P intersect the sphere at exactly 2 points, -P and P. So if Fp is not equal to P, then Fp cannot lie on this line through the origin. In particular, the line connecting Fp and -P cannot pass through the origin, so here this norm is never going to be 0, and thus this is a well-defined homotopy between F and antipodal. But we know that the degree of the antipodal map is just -1 to the n plus 1. So if F has no fixed point, then that must also be the degree of F. That is a pretty neat result, right? Now we're gonna use this to prove another pretty cute result about fixed point. Alright, so suppose that G acts freely on the even sphere. Let us show that G must be the group Z mod 2Z. Now, since elements of G are just homeomorphism on the even sphere, we can define a degree map on G just given by taking degree of each element view as a homeomorphism on S2K. Now, since G acts freely on S2K, by our previous result, every element of G must have degree -1 to the 2K plus 1. And here's where we use the hypothesis that this is an even sphere. So the degree of every non-identity element of G must be -1. This means that there is only one element in the kernel of the degree map, namely the identity. Thus all fibers must have size 1, and therefore, by first isomorphism theorem, G must be isomorphic to Z mod 2Z. Thus the only group that acts freely on the even sphere is Z mod 2Z. And that concludes our discussion about fixed point.